Podem perguntar em português ou em inglês, tanto faz. Ok? Alguma pergunta da última lecture, das últimas lectures, qualquer uma? Or any questions? No? All right. So let's continue. Let me share my screen. So at the end, I decided to go straight to direct detection instead of discussing kinetic decoupling, because I realized that in order to cover kinetic decoupling, I would not be able to cover in one lecture. We'll need to cover in 2 lectures, and then the week would be over. And then Patricio is leaving next week, so I decided to. I think I would drop the kinetic decoupling. It's too technical. Yeah, I'm gonna share my notes. All right, so let's begin. So we've seen so far. Let me continue with this 4th lecture right here. So I was discussing towards the end of last lecture was the threshold, just to recap a bit. So the last lecture was about the 3 exceptions to the relic density calculation. So as we've realized, the relic density is the relic density for cold dark matter is inversely proportional to the thermal cross section. And this is true, continues to be true. Okay, this doesn't change that. The point is the naive expectation you get from this formula only in red is broken, because this sigma v might experience some effects, such as the resonance. So you might have a sudden spike in the. It might have a sudden spike in the sigma v. So eventually, as you know, as you increase sigma v, so increasing perhaps the mass of dark matter particle, then the abundance should decrease, but eventually you'll reach a point where you have a resonance and then has a spike in the cross section. Then the abundance might change by orders of magnitude all of a sudden. So that's sort of an exception, but it's not an exception to the formula. It's just an exception to the behavior that you expect. Okay, and we also discussed the threshold effect, which has to do when new channels are opened. Okay, so as soon as you in the early universe, as you get the thermal contribution to the center of mass energy, therefore in the early universe you might have processes that dark matter can annihilate into, but today they are not present because of kinematics. Okay. And the third one, which was towards the end, I'm going to recap again to go slowly, has to do with co-annihilation. So co-annihilation is the fact that when you have models where you have more than one dark matter particle, or you can have also dark matter or dark sectors, dark particles, which are not necessarily dark matter. So let's say I have a light scalar or a light fermion, which happens to be the dark matter particle, and another particle which is called dark. It's not dark in the sense that it's a dark matter candidate. It's simply because it has the same symmetries that the dark matter particle have. That's what means dark, okay? So we have a dark sector or a dark symmetry. So if in this case, let's say dark matter fermion, the dark matter particle is a chi fermion, and in my model, for some reason, I have 2 other particles that have the same symmetries that the dark matter particle has, let's say chi1 and chi2. In general, in principle, these 2 particles, chi1 and chi2, might contribute to the dark matter abundance in the way that chi1 might also has similar symmetries as the dark matter particle, has similar interactions as the dark matter particles. then will freeze out around the same time. And then as it freezes out at around the same time as the dark matter particle, it will eventually decay into the lightest dark matter particle around. So then we'll contribute to the abundance of that dark matter particle. It might be in one way or the other. So let's say that chi1 decays, chi2 decays into chi1 and chi. Okay, chi2 decays into chi1 and chi. Chi is dark matter. In this sense that chi1 will increase the dark matter abundance, right? And then chi1, and then again, eventually will decay into chi again. But chi1 is not stable. The only stable particle is the lightest one. So when chi2 freezes out and decays, increases the dark matter abundance after they freeze out. Okay? When chi1 decays, there are two effects. So let's say chi1, so I'm just take one more page here. Let me increase, let me zoom. Yeah, I'm gonna use this one. So let's say chi1, I have chi2. Let me go back to the yield. N over S, and then you have the curve. And this for dark matter goes like this, chi, and then decouples. So that's chi, the dark matter. Dark matter particle. Let me zoom in. Yes. Then you have another particle, let's say chi1. And chi1 then goes here like this, and then freezes out around here, and that's chi1. And I might also have another particle, let's say chi2. Let's say chi2 now decays, freezes out right here. I have chi2. So in this case, the yield of chi2 is larger than the yield of chi at freeze out, right? And x and y of chi1 is smaller than y of chi at freeze out. So therefore, if chi1, so now let's go. So I'm just contemplating assumptions, okay? I'm not having I don't have a concrete model. So if chi1 then eventually decays into chi2 plus chi, it means is chi1 will increase the dark matter abundance, right? Fine. However, if chi2 decays into chi plus some fermion or some standard model, what it does is, at the same point, at the same rate at which increases the dark matter abundance because it decaying dark matter abundance, but if chi2 is much heavier than the standard model particles, though the standard model particles produced from the decay of chi2 are relativistic. If they are relativistic, you already know they contribute to what? To the entropy. Right? In that sense that, okay, I'm increasing n chi because chi2 decay into chi. I increase the dark matter abundance, but at the same rate, I also inject entropy into the universe, and then the ratio will be the same. You see? Obviously, it will depend on some degrees of freedom. Remember, the entropy depends on the degrees of freedom. Okay, so what I'm saying is, at the same rate you increasing n chi, you also decreasing the yield, which is the abundance in the end, right? Related, because you also increasing the entropy. Okay, that's my assumption. If chi2 decays into chi plus n model. However, if the mass difference between chi2 and chi is small, as it is for co-annihilation, okay, then there is no entropy injection. I'm just simply increasing the number of after the freeze out. Let me close this WhatsApp. Okay. Make sense? Okay. So as you see, depending on the co-annihilating particle I have, remember, co-annihilating particles are particles that appear in the initial state of the equation. So annihilation is chi going to Fermi. In other words, I have dark matter going to something, standard model plus standard model. If there is any particle which is sort of stable or long-lived or has same quantum numbers that dark matter particles have, I call it co-annihilating particle. So I have a maybe dark chi1 and chi2 going to standard model, or chi1 going to standard model plus standard model particles. I can also have chi2 going to standard model plus standard model. Could be whatever in the final state. But as long as I have dark particles in the initial state, I call them co-annihilating particles. I also have chi1 with chi going to standard model plus standard model. I can also have chi2 with chi going to standard model plus standard model. Okay? So I have all these possible co-annihilation channels. If I had two co-annihilating particles, all of them will change the relative density. Might change the final abundance of chi in the end of the day. Okay? Think of the following. So look at this. So if I had just chi going to Fermi or standard model, if I had just this one, so let me just include this one. So that's the one I had from the very beginning. Without co-annihilation, the only thing I have is the one in black, chi going to standard model plus standard model particle. Okay? Chi bar. Or whatever. If it's a scalar, I could say chi. It's a real scalar. There is no entire real scalar. It's just a real scalar. So I'm saying in general, chi. All right. I have this. Then I solve the Boltzmann equation the way I did in the past lectures. Fine. If I had other particles that have similar masses or similar interactions, then remember, how is the freeze out of dark matter particle happens when the rate equals the expansion rate, right? But the only rate matters is this one, chi standard model. Okay? For instance, chi bar annihilating to plus E minus. That's an example. Okay? Fine. That's the rate. That's the only rate. But now I'm including an extra rate, which is the one, let's say, chi1 and chi2. But say, for now, does this matter? Yeah, it matters because at the eventually you produce chi. So you have to plug that in the Boltzmann equation. The Boltzmann equation tells you the evolution of the number density of chi from all processes. Whether it's coming from the decay of something else, whatever, from annihilation of something else, you have to include all of them. Okay? So the Boltzmann equation will get really complicated because the Boltzmann equation just tells you what is the number density of the particle that you're interested in. Okay? How it's changing with whatever interactions you can think of. If I had just the one in black, that's the only rate I should account for. However, if chi1 goes into a standard model, then at the end of the day, I might also produce n chi, right? So I have to plug in that chi1, chi2 rate. Also, I have to compare it with the expansion rate to see how is going to produce chi at the end of the day. Okay?
Just to be precise, in this case, the Boltzmann equation, we have to take into account processes that change the number of chi, right?
That's right.
I have seen an expression
for somewhat like an effective cross-section of coordinations in terms of the...
I'm going to show it just below.
Oh, okay, okay. In terms of splitting mass.
Okay? I'm just trying to give you the reasoning.
So normally there are these two particles or more?
Could be more. I picked one. Usually there are few. So for instance, there are models such as very big models like SUSY, supersymmetry, there are many particles, but usually there are not many. Because the mass splitting, as you're gonna see, has to be small. So okay, what are the chances of having many particles with roughly the same mass?
Okay, so this mass splitting is between the two masses that is not
mass splitting between the coordinating particle and the dark matter particle.
Oh, I see. So it can be 1, and the mass split must be equal to have this coordination effect.
So he's asking what are the mass relation between the coordinating particles and dark matter mass to be effective. So the mass of the coordinating particles have to be within 15% of the dark matter particle mass. So let's say it's 100, then 115. So if it's more than 115, the effect will be negligible. Okay, so 50% at most, close to the dark matter mass. Okay, the mass difference has to be around 15% of the dark matter particle mass. That's roughly what we get from solving the Boltzmann equation. When we see it, when you increase more, you have the effect is very negligible because of the Boltzmann suppression. Because what happens is the number density of particles, non-relativistic particles, after the freeze-off is exponential minus m over t, right? So if I have another dark particle, I have m chi2 over t, right? And then what it matters at the end, how much this is going to affect the inner chi I had is proportional to the m chi2 over t. So when you solve them into the Boltzmann equation, what it matters is exponential of minus m chi2 minus m chi over t. So if that mass splitting is large, there's a Boltzmann suppression, exponential, right? So the mass splitting has to be small in order to have some minimal effect on the number density. Okay. So, and for instance, as you see, remember the freeze-out happens when h is equal, the rate is equal to the Hubble rate. For this case, and again for here, but now I have one rate, another rate here, another rate here, another rate here, another rate here, and the sum of all of them plus this one has to be roughly the Hubble rate. But they might be different because they involve different particles. Therefore, this will affect at the end, when I solve the Boltzmann equation, what n chi will be at the end. You see?
I don't understand the logic summing. I don't understand why you have to sum to be equal.
Yes. And so if I have it here. In lecture 3, let me see if I have it here. I have here. No, lecture 3. And pick one formula, this one. So that's what it is. So let me zoom in. Oops. I could pick this one, but I want to see this one. It's easier to see this one, this way. This one. So that's a Boltzmann equation. That's the evolution of the yield, the number density, as a function of the yields. Okay? It's a coupled equation. So it depends on sigma v. Sigma v, remember, rate is n times sigma v, right? So that's the rate, right? Divided by the number density. That's what it is. This sigma v is the total sigma v. So what you have to do is so at the end, so let me even go back further. Let me see if I can have it here. Here. So that's the one you've seen books. That's the derivative in time of the number density of chi. Number density of chi depends on the exponential rate, and plus the sigma v of chi going to Fermi. That's the number density of chi, and that's the number density of chi in equilibrium and not in equilibrium. Okay, but then you have, let's say that you have another process, which is chi1 going to whatever. Then you have another one here, n chi plus a and chi sigma v. Which sigma v? Chi1 chi going to standard model, and then you have the same equation. Repeat. Which other process? Another one, another one, another one. For each sigma v, you have another one, another one, another one, and another one. And then this is the same. I take this, integrate out, put it outside, and that should just sum the cross sections.
Yeah, but I understand why you sum when you involve chi directly. But why do I have to sum when I involve those processes chi1 and chi2?
And so, friends, look at this. For chi1, this will be chi. This is the number of chi. How much chi I'm going to produce. But then, in this case, this will only contribute to the dark matter abundance if I produce chi in the final state. If I don't produce chi in the final state, this is no longer sigma v. That has to do with the decay rate of chi1. And this equation changes. So this equation for when you produce it from annihilation, I'm not producing chi. If I have chi1, that's the process I had. If I had chi1 chi producing standard model, I'm not producing chi, right? If I produce chi from the decay, I have to include not this, I have to rewrite this equation in terms of the decay rate of chi 1. But also have to include the chi1 annihilation rate. I have to include both, because I have to now take into account the time evolution of chi1 as a function of time. But chi1 is like this. Okay, I solve it for n chi. I find n chi. Okay, fine. But n chi can be produced from something else. At which point is it going to be produced from something else? Well, I have to solve the n chi1 function. Then I solve the n chi1 function, which depends on what? Is it stable? No, it's not stable. It has a lifetime. So I have to include the annihilation and the lifetime. Okay? So both. I solve for n chi. Once I solve for n chi, that will feed into the first equation for n chi. So it'll be a double coupled equation for the number density. The more particles I have, the more I have to solve them and then plug that in back into the n chi equation.
So even those with chi1, chi2 going into standard model, they have to account into this equation?
Because I need to know what is the yield. For instance, that's why I was not even focusing on the equation. I was focusing on the figure. Here. So, for instance, the one we had here. Okay. Where I was? Here. I don't know. And look at here. So we said that chi2 decouples there, right? How do you know that chi2 decouples there? I need to solve the Boltzmann equation for chi2. And how do you know how much chi2 that is right there? I need to solve the equation for n chi2. And when does n chi2 decays? Well, I have to solve the equation for n chi2. I need to know how much n chi2 that is at a given point in time. So I need to solve the equation for n chi2. But n chi2 and chi1, they are interacting with each other. So they interfere on each other. It's not n chi2 survives independently of n chi. I said that they share similar interactions, right? If they share similar interactions, the processes that involve chi1, involve chi2, involve chi-n, whatever. So they are all coupled. Okay? That's very different. Let's say, now I have a particle. I'm assuming it's long-lived. Has nothing to do with chi. The interaction that chi2 has nothing to do with chi. Then I solve the Boltzmann equation for n chi2 like I would do it for chi. And then now assume out of thin air, well, now I'm going to assume also that chi2 decays into chi. And the only thing you need to know is when it decays. And that's what I also did in papers in the past. Okay, we write papers. We wrote a paper where you assume that there's a long-lived particle that eventually decays into dark matter. It's an assumption. But in reality, you have to solve the full Boltzmann equation and say, okay, if you're saying chi2 decays into chi, then chi2 interacts with chi. So you have to solve the Boltzmann equation, all of them together. You see? And if, look, and think of this. If chi2 interacts strongly with chi, then they'll decouple roughly at the same time, because they will remain in equilibrium with each other for a long time.
Depending on also, depending on the dynamics of the fields and particles that you are interested in, if they, for example, introduce entropy in your system, you have also to put in equation the Boltzmann equation for the entropy too.
Yeah, that's what I discussed before you arrived.
Maybe I'm just not getting it correct. Can you go a little bit? Yeah. So I can see how why you should put those chi1, chi2, chi going to standard model. Because I mean it's chi, it's involved with chi. But chi1 and chi1 and chi2 going to standard model. Why does that? I don't see how that would contribute to the number density of chi itself.
Because I'm assuming chi1 decays eventually into chi.
But even if it's going to standard model.
But that's annihilation, not decay. So there is also one, which is the decay of chi1 goes into chi, which I did not include. So should be also there. So you should not solve just this one independently. You should solve for both. And I'm going to assume it's why you should care about the annihilation if it's not producing chi. That's your question. The question is because it tells me that when chi freezes out. So that equation tells me when chi freezes out, and then when chi will then decay into chi1 will then decay into chi. Okay? So one is just tells me, look, if I just included chi1 decays into chi, and then I ask, okay, what was the abundance of chi1 in the first place? Tell me. The only thing you know if you just include that one.
Okay,
you see? You got it? So if chi1 decays into chi, and the chi1 abundance is irrelevant, so what? That chi1 decay into chi is not abundant, I don't care. If the abundance of chi1 in the end after the freeze out is 10 to minus 4, it decay into chi, so what? It's 10 to minus 4. The abundance of dark matter is 0.1. 10 to minus 4 decay into chi, it could be everything. It won't mean a thing for dark matter. I need to know the abundance of chi1 to see if that's really relevant when it decays, produces dark matter. But to do so, I need to solve the abundance for chi1. Make sense?
Yes.
If I want to calculate the rate of chi1, chi2 to standard model particles, so the rate includes number density. So the number density is the number density of chi1 or
both?
Chi2?
Both.
But how
I'm gonna show the expression later. Okay?
Yes.
That's the logic. The logic is the key thing. The rest is mathematics. Okay?
All right. Okay, could I include, just last question, could I include a particle that decay, because in that equation, basically the decay into chi dark matter would be only significant after freeze out, right?
Not necessarily.
Okay. I was going to ask if I could include a particle that decays into chi before freeze out significantly. Like, could I do it?
It could do.
That's because if it decays before the freeze out, it could contribute to a kind of non-thermal production of the dark matter. So when the dark matter decouples from the bath, it will be like a bath production, non-thermal and thermal, and the abundance will be sum up.
Oh, okay.
But again, you have to include in the equation of chi.
Yeah.
Now you have to include just
But
the equation of chi.
The equation would be another, because now you're just talking about non-thermal production. So
Okay.
the dynamics is different.
So if there is any particle, their question is, if there is any particle that decays into dark matter before the dark matter freeze out, how do I take that into account? That's the question, okay? So the dark matter abundance can be governed by annihilation and by decay of anything. So let's just give a step back to understand. So why I'm including, to compute the dark matter abundance, I'm taking into account chi going to stenomotor, instead of stenomotor, chi. Because I want to solve for the dark matter abundance, what produces dark matter. So why I'm doing chi stenomotor instead of stenomotor, chi. Because chi produces stenomotor, so there is no dark matter in the final state, right?
Yeah.
There's no, which is similar to the question you asked. So the reason why I have chi going to stenomotor is because you assume from the very beginning that you had an initial abundance of dark matter, and we will be diluted with the temperature, right? Remember, the yield for non-relativistic particles is exponential minus m over t. So I know already the abundance, any given temperature. However, because of the freeze out, this abundance changes. Changes because of what? Because of the expansion rate. The expansion rate equals the interaction rate. Which rate? The rate at which stenomotor, two particles stop existing to create two stenomotor particles. If this process was not there, I just know the dark matter abundance is exponential minus m over t. Tell me the mass, tell me the temperature, I know what's the abundance. But because I had two and they are no longer two, there's a change in the number density, right? If this annihilation process was not present, I would know the dark matter abundance at any given time in temperature. But it's changing. I had two, nothing. Two, nothing. So I'm diluting the number density of dark matter particle. And if there was no expansion, let's say no H, then we'd go to 0. So because there is a change in the number density, I have to take into account which process that changes the number density. The number density as a function of time, as a function of temperature or time, I know. But now there's a number changing process. I had two, nothing. Two, nothing. So this change, that's why I include chi bar going to stenomotor. Okay? It was just a dilution, exponential dilution by the Boltzmann, or no, right? But now I'm changing the number via process, chi into something. Okay? Fine. And now going back, so if I had, again, 2 into something, now if I have also something decaying to dark matter before the freeze out, if you want to do it properly, you have to plug that into the dark matter Boltzmann equation. So for instance, that's one of the it's a research project, okay? It's not something easy to do it. For instance, Jacinta and I, we wrote a paper where we assumed there was something that decayed into dark matter after the dark matter freeze out. So the dark matter freeze out occurs in the simple way. The only way I can know the number density is just, okay, if there was no change, 2 to stenomotor, nothing, 2 into 0, I would just, the number density would be exponential of minus m over t. But because I had 2 into stenomotor, 2 into nothing, have to include that in that sigma v into the equation. And then I solve, I get the result, get the final abundance. But now, if there is now you're assuming there is another particle that decays to dark matter, properly, what you should do is you have to put in the lifetime of that particle inside the n-chi equation. Okay? You have to plug that in because that's also a function of temperature. It just doesn't decay whenever you want, because then remember the lifetime is 1 over this rate, decay rate. But the decay rate depends on the number density, but the number density is a function of temperature. So you have to plug that into the n-chi equation. What almost everybody does, including myself, I forget that and just assume decays later. But
because the cross-section that appears in the number density equation is the cross-section
thermal.
Chi going to something else, right?
Chi going to something else.
Where do I put in the number density equation this term of a particle decaying into dark matter?
You include another term, which is
A sum.
a sum. You have this one, then you put another term, and let's say I had n dot equal plus 38n, right? Equals sigma v, that is n squared minus n squared, right? That was the equation. Then you include another one, which is plus the rate, because the rate is one of the lifetime, or the rate. Number density, not the number density squared, because I have just one chi, minus n-chi in equilibrium minus n-chi without being in equilibrium.
Yes, I think because he was not here yesterday, when in the seminar of Patricio, that he showed that in his paper he had to calculate a lot of different processes.
Yeah. So first he had a scenario similar to what you were asking.
So he had in the paper, I mean, you have a lot of processes that will contribute to plus or to minus in your Boltzmann equation. Then you have to include it like a just source term.
Yeah.
And okay, and then I asked as an exercise for you to prove it. So this is a so that will be the 4th exercise, exercise 4, right? Because I already sent a list with 3, so that would be a 4th. Prove it that everything is here in this equation. A very famous paper by Gondolo and Adso, very famous. They were both postdocs at that time at the Max Planck Institute in Munich. So what it does is the following. So instead of having a sigma v, when you do have co-annihilation particles, you average the sigma v you had, the sigma cross section, times this exponential suppression. I'm going to explain what it is. So the exponential suppression has to do with the number density. And then you weight with the also number density multiplied by the degrees of freedom. So there are some steps to go from the sigma v to this sigma v effective. And this delta m is the mass difference between the dark matter particle and I or J being whatever co-annihilating particle. So let's just focus on one, okay? So let me erase this. Let's forget this one for a moment. So the notes I sent to Clarissa through WhatsApp in our group today does not include this mass I'm making now, okay? So let's focus on this. So I have delta m over t. So as you see, if I have a co-annihilating particle chi1, which is much heavier than chi, delta m is large. If delta m is large, there's a suppressed abundance contribution to the dark matter abundance at the end. So if the dark matter, this sigma v effective will be small, okay? So it means is the cross section, remember, omega h squared is proportional to 1 over sigma v average, right? So let's say I have the contribution of one process plus the process 2 plus the process 3, all of them. And the one which involves chi2, the co-annihilating particle chi2 is here. This is just the canonical. This chi-chi going to fermion-fermion. This is chi2 in the process. This is chi3 in the process. So if the mass of chi2 is much larger than m chi, then this contribution is Boltzmann suppressed. And this chi3 is much heavier than chi, then again, this contribution will be Boltzmann suppressed. And what you get at the end is just the canonical one. Okay? And I say, okay, Fernando, where does this 15% comes from? So it comes from when you usually pick models where G is the degrees of freedom of that particle, which cannot be far from 2. Okay? So I have a fermion, it's spin 1 and down, up and down, right? So if you have polarization bosons, you can have up to 3, maybe if it's a massive gauge vector boson. So maybe 3, but that's it. You don't have more. 3 polarizations, right? Photon, 2 polarizations, that's it. So it cannot be far from 3. So even if you take 3, and that's you take the canonical value of the cross section that gives you roughly the cross section. So you take this 3, and what should be the delta M, knowing the freeze out of dark matter, should be around 20 or 30 or so, right? That's it, right? That's what it is. The temperature of the freeze out. Remember, X is equal roughly 20. But X is M over T. Therefore, T is equal M over 20. So for dark matter particles at around the weak scale, from going from 100 GeV to 1 TeV, you know that G is maybe at most 3, and then you plug in that equation, you're gonna realize that the delta M should be small. Okay? So I know T, the temperature. Okay, I know the temperature. I know that G is almost 3. You take one co-annihilating particle, and then I say, okay, take the ratio of this equation, multiplying by all the degrees of freedom. This delta M should be roughly 15% of the dark matter particle mass. 10%, 15%, maybe 1%, depends on the masses. But whatever, they should be close to the dark matter mass. Depends on the G you take, depends on the temperature you take, but delta M has to be small. And that's easy to see because of the exponential factor. Okay? Make sense? Fine. Okay, so that's what I asked you to prove it, to prove this equation. And the derivation, the explicit derivation is in this paper. This paper has, I don't know, 800 citations, 900 citations, something like this. It's quite famous.
You put this reference in the group, right?
I just sent this. No, I sent yesterday the lecture note.
The lecture note?
Yeah, I sent yesterday in the group. Lecture 4.
Is this exercise for tomorrow?
No, this exercise is for Thursday next week.
The other one is, oh, okay.
The other one's for tomorrow.
But I mean,
This one is for Thursday next week, or Friday. Let's say call it Friday.
let me take this. Okay, because you put two archive.
No, this is something else. I'm gonna show you. So this is to prove it. Prove it by Friday. Friday next week. Okay. All right. So that's what I had to say about the exceptions to the relative density. But I want to just name one more. So which is called semi-annihilation. Semi-annihilation is just a name at the end. So let me take the process that I was discussing before. Hold on. Here. So as you see, I did it on purpose that I had chi1 and chi2, just dark particles in the initial state and no dark matter particles in the final state. If I happen to have a dark matter particle in the final state, I call this semi-annihilation. It's just the name, but okay. Just semi-annihilation is the fact that now you have chi being produced. And then again, we change the Boltzmann equation and have to do everything again. Okay. Now let's go to direct detection. Any questions? All right. No? I'm recording, right? Yes, I am. So the scattering rate is, I'm going to try to derive the formula of scattering rate. I think this is quite nice to see it. Because I'm telling you, for the first time, when the first time I read it, I struggled in deriving this formula. So I want to show it. So the scattering rate is simply the number density of scatterings, or number, divided by the number of kilograms per second. And why I'm going to do this? So usually when you're referring to detection techniques, whether it's direct detection, whether it's indirect detection, you always normalize by the exposure. What is exposure? Let's think of this way. Let's say I have a detector as the size of this remote. It's made of metal, metal and plastic. And then I have another detector, which is this one. It's just plastic. And then I have some flux of dark matter particles coming in. If they are made of the same material, well, they are not, but if they're made of the same material, obviously I'll detect more scatterings using this one than this one. But then it doesn't matter how many scatterings you observed. What it matters is how many scatterings you observed per second per kilogram, because that's what the fundamental quantity is, the scattering per kilogram per second. Because obviously if you have a larger material, you're going to detect more. But how do I know that my result is consistent with yours? I have to normalize by this how much kilograms you have and how much time did you observe, right? Because if I observe for a year, I'm going to have a number of scatterings which is different from you that observed for a month. And I need to make sure that my results consistent with yours. Well, it's the same dark matter particle coming, right? So they have to be consistent. That's why I normalize by the number of kilograms and normalize by the number of time, the measure of time, which is days in case of direct detection experiments. Okay, you don't normalize by second, you normalize by days. Make sense? For indirect detection, as you're gonna see, they measure by the same thing. So if you have a satellite is usually a box, a cubicle. It has some, 1 square meter in area. And you measure, this telescope is there observing the sky for a year. So the exposure will be 1 square meter times 1 year, if I'm observing that region. But if I have another telescope somewhere else that is detecting the cosmic rays arriving at the area of the telescope, so I have to normalize by the area of the telescope and how much time you observe the same portion of the sky. Okay? And it's not just proportional to this, also to the size of the sky that you're observing, right? So I'm observing a small portion of the sky, I have a smaller exposure. I'm observing a large region of the sky, I'm observing a large exposure. I have a large exposure. Okay? Because I'm measuring fundamental quantities. So it matters how much time you're observing and the area you're observing for indirect detection. For direct detection, matters the size of your target and how much time you use that target. Because the more targets you have and the more time you have, obviously more scatterings you're probably going to see it, right? And I have to make sure that what I measured is consistent with you somewhere else, another place in Earth, with a different detector, with a given different size, and you ran just for 3 months, right? And that's exactly what happens in practice. So different detectors, they measure scattering rates in different times. It happens a lot on a daily basis that people are planning to measure scatterings for a year, but during holidays, there are very few people around. If a detector breaks, they have to stop taking data. And when they come from vacation, then fix the guy who is really expert on fixing stuff, comes back from vacation, then fixes it and starts taking dating again. And then I have to normalize by the time off. So I didn't take, I had 1 year of data taking, but it was not actually a year, it was, no, 11 months of data taking. And that 11 months of data taking, if the next year, for some reason, I take for a year, these two results have to be consistent with each other. And the only way to make sure they're consistent is normalizing by the time, the exposure. Make sense? Awesome. Okay, so the scattering rate, so the differential scattering rate should also depend. So this NT, as you can see here, is the number of target nuclei per kilogram of the detector. Okay? Soon I'm going to normalize it by second or by day. So N is the number density of dark matter particles. As you remember, rho, non-relativistic particles, N times M. Then N is equal to rho over M. Rho is the, so this is the number density, right? Number of particles divided by volume, right? In a given volume. So the number density, so when you write down this equation, what you write is mass is in GV, that's GV. So in rho at the end, so if you write it like this, rho will be number density, which is centimeter cube, mass is GV, right? So the density of dark matter is GV per centimeter cube, okay? In units. Fine? Awesome. And that's the sigma V is here, the cross section DE, I'm just getting the units right. Why is this here? Well, the larger the cross section, more likely the scattering rate, right? The larger cross section, the larger the scattering rate. So they should be proportional, fine. But as you see, the units are not correct because I still have to normalize by time somewhere, right? That's what the scattering rate is. Okay, fine. Soon I'm going to back to that. I need to normalize by time. Just remembering what I did here, I just replaced N by rho over M. Okay, for non-relativistic particles. Fine. And I just want you to remember that the velocity distribution of dark matter, which is Maxwell-Boltzmann, the integral of minus infinity to infinity depends on how you do it, or to infinity to from 0 to infinity is normalized to 1. Okay, you normalize it the way you want, from minus infinity to infinity or from 0 to infinity. It depends just the, so you just change the normalization factor of the distribution function at the end of the day, right? So it's exponential of minus v squared. And then the way you define the normalization, you just change the normalization factor in front of the distribution function. But okay, fine. So let's do it. So the rate is the rate of scattering. That's what it is. The rate of scatterings for a given nucleus per kilogram per day. But the rate in particle physics or in statistical mechanics or in fluid dynamics, whatever, is given by the flux of whatever times the cross-section of whatever times the number of target nuclei of nucleus or nuclei you have divided by kilogram. But look at this. If I work out the units as I just did, so the DRDE is the number of target per kilogram, is here, 1 over kilogram. This one, we just saw it. So the number density is 1 over a centimeter cube, right? I just multiplied divided by GV. This sigma is the cross-section is centimeter squared, and DE is GV. Okay, when I work out the units, what I get is 1 over kilogram, 1 over centimeter, because the centimeter squared cancels out with this cube. This is number 3, and 1 over GV. But as you know, I want the scattering rate to be 1 over the kilogram, 1 over the second. That's the scattering rate. And this energy is this GV. So rate should be 1 over kilogram, number of something, per kilogram per day or per second, okay? Per day or second. Well, and there is a GV here because I did DRDE. In order to get the units right, so 1 GV kilogram per second or per day, if you think about it, what I need to do is, remember, let me go back here. R should be something proportional to 1 over kilogram per day or time. Let's put it time. But my unit is giving me, here it is. What I'm getting from this equation is that, look at here. Let me erase it. What I'm getting from this is that dr, my r, scattering rate from this formula, is giving me 1 over kilogram per centimeter. So if I happen to multiply this quantity by a velocity, which is centimeter per second, if I multiply the scattering rate by some velocity quantity, this centimeter will cancel with centimeter, and second with second, which is exactly what I wanted in the first place, which is the scattering rate that's 1 over kilogram per time. So the scattering rate, what we do is, we started, let me go back. As you see, we started like this. Number of targets per kilogram, here it is, per kilogram times number density times d sigma dE. But in order to get the per time, also normalization, I have to include the velocity here in the beginning. And that's what we do. So we include the velocity. So the scattering rate is the number of targets per kilogram per second I have.
In this case, this is the relative velocity between the target and the dark matter particle.
Exactly. V is the relative velocity between the target and the dark matter particle. And sigma, the sigma d, is the scattering cross section. But there is something missing. Look at this. So I need to average this function. Why? Because I don't have a velocity. I have a distribution of velocity, right, which is Maxwell-Boltzmann. So I have to take the average of that in a Maxwell-Boltzmann distribution. And why I'm including this sigma dE also in the average, not just the velocity? Because we realized the cross-section, just the cross-section, the scattering cross-section might also depend on the velocity of the incoming particle or the relative velocity. Even the scattering, not just the annihilation. We realize for annihilation this is true, but for scattering it's also true. Let's say, oh, for now I can't see this. Okay, let's say that you can't see it. So let me use this thing, this spacing here below. Remember, my notes don't have this mass, so it's less messy than now. So what we did was this: chi going to something. Let's see, z. And then ferment, anti-ferment, right? That's what we did. Now I'm gonna flip this diagram. Chi, z, ferment. This is a scattering, and this is annihilation. So if this one does depend on the velocity, might depend on the velocity, as you know, that sigma v might also depend on the velocity. Also, the scattering might also depend on the velocity. However, the momentum, the energy at which those processes happen are completely different. One has to do with the expanding universe. And the scattering I'm measuring today. Okay? I'm measuring the scattering today. Now, has nothing to do with the expanding of the universe and then the scattering happened today. It's happening today. The velocity today. Okay? So it depends on the velocity of the dark matter particle in our galaxy today, not in the past. Okay? Fine.
Let me ask you something, please.
Yes.
Just after this goes, so in this equation, we have that the number density of dark matter particles would depends on the energy, right? So why
The number density will depend on the energy?
Yes, somehow.
No. This any density here will now be the local density of dark matter particles.
Okay.
So we are at the sun.
Okay.
So what is the number density of dark matter particles at the sun? That has been measured by measuring the velocity of the stars in our galaxy. Okay. Okay, so fine. Okay, and then what is the average of a function? Well, the average of a function in a Maxwell-Boltzmann distribution, I just integrate that function, which is this v times d sigma d integral of the velocity distribution in 3D space. Okay? And this is what I had already before. N chi is rho over m, right? That's what I hear, n over m. And this ME is because it's in Portuguese, matéria escura, okay? Okay? All right. And I'm going to explain what this V min is soon enough. Okay, so that expressions, that's what you're going to see in papers, in books, that's expression right there. So this deduction is not, well, I haven't seen it. I think I saw in a lecture note quite some time ago, and I wrote it down because I knew that was really nice. Okay, so what's V min? Let's understand it. So the way it goes as follows. So I have a dark matter particle chi. It scatters off a nucleus, which is at rest in my detector. It's here, stopped, right? I have the detector in a tank. It stopped. The tank's not moving. Well, it's moving because the Earth is moving. Let's say there is the relative velocity. The relative velocity just dictated by the velocity of the dark matter particle, basically, right? Okay, and there is also the velocity of the Earth, but let's not consider this for a moment. We're gonna use it this relative velocity of the Earth soon enough for other things. But let's say the nucleus is at rest. Right. So comes a dark matter particle, has some kinetic energy, has momentum p, as I wrote there. The nucleus might have some momentum. I am writing a kt, k of the target. And then this dark matter scatters off the nucleus and then goes away with momentum p prime. And the nucleus now gets a momentum because of the scattering of the dark matter particle, and the momentum I'm calling kt prime. So the transfer momentum pq is the p prime minus p. That's the momentum transferred to the nucleus, right? There are some ways you can do this. I'm going to do it this way. So in the center of mass frame, the p is the initial momentum is equal minus chi t, right? Because in the center of mass, they have exactly opposite momentums, right? And also, in the center of mass, p prime is precisely minus chi t prime. Okay, then you work out the formula, you not deduce it. And the only thing I have introduced now is the reduced mass, because as I have a two-body system, it doesn't matter just the mass of one particle. I have the mass of the two. It's like a two-body system. What matters for the center of mass momentum is the reduced mass, right? Awesome. For elastic scattering, I'm going to assume that the module, well, elastic scattering, the module of the p momentum is equal p prime. And then you just play with these formulas. I won't deduce it. You get the transfer momentum is equal to p squared 1 minus cosine. Where is cosine theta? Theta being the angle, the scattering angle between the initial state, initial state nucleus and the final state chi. Just define it as theta. And when you work out the formula, you get that this momentum is transferred in terms of the reduced mass. It's 2mv squared times v squared 1 minus cosine theta. Now let's understand something really important. Okay, this is just formula, kinematics, and so on. You can work out the detail later. Okay, so looking at this formula, it means is when theta is equal pi, that's when you get the maximum momentum transfer. Okay? Fine? Awesome. It means is if the maximum momentum transfer is the most efficient transfer of energy. Okay. The energy transferred, or the energy recoil, is the same thing, is momentum transferred over to mass of the nucleus. And this is, well, I just use Q as this formula. I get this one. This is just, there is no, it's just a parenthesis here, okay? 1 minus cosine theta. And then if theta is equal pi, then that you get the maximum momentum transfer or the maximum recoil energy, the energy which is really devoted, put it into the nucleus. Therefore, when the energy is the maximum, reaches the maximum value, if I just look at this equation, means that I can find what's the minimal velocity I need to reach that energy, right? So if the scattering angle is right, that's the minimum velocity I need to give exactly that recoil energy. Okay? Why I'm talking about this? So that's the V min. So what it means is, if I have a target and the minimum velocity, what's the minimum? Remember, dark matter particles have a distribution of velocities. And let's say that my detector, for some experimental reason, can only detect recoil energies above 1 keV. 1 keV. I can only detect energy above 1 keV. Okay? For some reason, my detector does not measure energy too small. Then I can say that, look, my detector is invisible cannot see any dark matter particles which have a velocity below something. Okay? Why? Because maybe those velocities are too small, will produce an energy, but I can't see it because my detector, for some experimental reason, cannot see energies below a certain amount of energy threshold. We call energy threshold. It's the energy at which below that I cannot see anything. I don't see a signal. I can only see a signal if the energy, or the recoil energy, is larger than the energy threshold of my detector. What tells the energy threshold of the detector? Well, the detector itself, what it's made of, or no techniques, the wire, or whatever. Okay? So it has to be above the energy threshold. And different detectors, which are made of different things, they have different energy thresholds. Okay? Now think of the following. If I take the velocity distribution of the Maxwell boson has a tail. If for some reason that scattering took place when for the dark matter particles that have very large velocity, that particles will produce a signal in any detector. Because they have a large velocity, they will produce a signal anywhere. But if for some reason that distribution velocity picked a particle, the particle had a probability of having a different velocity, right? If that particle came with a different velocity, which is very small, some detectors will see a signal, some others won't. Simply because of distribution velocity. Just from this argument, you can explain why some detectors see a signal and why others don't. Wait, but I did not see the signal. Yeah, sure. So what? What's your energy threshold? So that goes now, what dark matter research requires is for you to go beyond theory. you have to now understand some technical aspects of dark matter. So you have to cross to the experimental view of things. It's not like, my world is perfect, the velocity is a constant, I know the velocity. No, you don't know the velocity, you know the distribution of velocity. And the energy threshold of the detectors are not the same, they're different. So dark matter research requires you to go beyond theory in order to really be a dark matter expert. It's not just constructing a model and solving using micromegas. Okay? It's not. So, okay, makes sense? Fine. So that's the minimum velocity. And just want to emphasize before I end today's lecture that the dark matter obviously cannot have a velocity larger than the escape velocity of our galaxy, right? Which happens to be around 550 kilometers per second. And the velocity of the stars, or in the solar neighborhood, is around 230 kilometers per second. And everything is rotating. The maximum velocity in module I might have is the sum of the two. Okay? Because I might have one going with the escape velocity, finding, let's say, another, if a velocity which is around the neighborhood, solar neighborhood, is the maximum. I don't know. I would say it's the maximum. That's the maximum I can have. It's, let's say, nearly 800 kilometers per second. Okay? So why I do this? Because you saw just a while ago that the scattering rate is this. So what I have to integrate is from Vmin to Vmax. Vmax is the maximum, is the velocity, escape velocity, plus some sun velocity. Usually people call it this, include this V-scape, but it's not V-scape, Vmax.
Smaller than escape. Smaller than escape.
Could be larger than V-scape. Because of velocity on the stars.
I see.
So you're saying that dark matter cannot surpass the escape velocity?
No.
Otherwise, it will be not part of the dark matter escape, right?
Yeah, one individual velocity of one particle cannot have a mass than the V-scape. But the relative velocity can be larger than V-scape.
Right.
Oh, okay.
Which is this V here,
Okay.
right?
Because you're integrating the dark matter escape.
Mm-hmm.
But dark matter particle, for any reason, I think, can have a bigger velocity and escape.
Sure.
So,
But it won't matter for direct detection. Streams. Streams. The streams. It's called streams.
Okay,
But it won't matter for direct detection if they have a velocity larger than the V-scape. Unless, for some reason, have a streaming of dark matter particles coming into the galaxy. And then, okay, how
the population is way
yeah, it should be small. But what he's asking is something else, okay? He's covering some topic that I'll cover later. Okay, about stream velocities. But at random, a smooth halo, there is no so like a spike of some random velocity. Well, our galaxy is not a sphere, perfect, everything is Maxwell Boltzmann, blah, blah, blah. Okay, might be for some reason that we don't know. For some reason, there is a region in our galaxy where dark matter particles might have a velocity which is I know, much larger than we expect. This region is called streams. It's a stream of water, you know, something injecting water, stream of water. So it's pointing towards something. And actually using cosmological data, this seems to be what happens. They might have streams of flux of dark matter particles in galaxies. People don't understand why exactly how this comes from, but it's consistent with data. But anyway, it won't change a lot. Maybe it's instead of being Vmax being 800, remember 500 something plus 200, right? So the maximum velocity you should have.
It's like
Maybe it'll be 900 or something. So you change the integral a bit. it won't change dramatically what you're gonna get at the end of the day.
It's a kind of net.
Yeah, so it's called a stream. But let's go to this minimum velocity. So when I saw this for the first time, and I have to be honest with you, so when I was a PG student, I had no idea about this. So I was half of my PG working precisely on dark matter, and I had no idea what V-min was. No idea. Well, because my PhD advisors were not dark matter experts. Everything I knew was just from reading papers from someone else. And in reading papers, you not understand this. So you need lectures. And at the end, I really advise you, there is some TASI lectures. At my time, they were recorded. So there were some TASI lectures recorded from the world expert dark matter guys who have been doing this since, since their undergrad. TASI. T-A-S-I. T-A-S-E. TASI lectures. So I watched several TASI lectures from Dan Hooper, Neil Weiner, Paulo Gondolo. So I saw these lectures. Catherine Fries. I watched all of them. And I watch, rewatch, because they would speak as what the hell this guy said. Because my English even back then was not that great. I said I would repeat over and over again until you get every single word they wrote. And I have notes in my office, is there. You can see I transcribed every single thing they said in a paper written. This was pause and I'll write, pause and I'll write, pause and I'll write. Because that was the only source of something like really pedagogical going from the beginning to the end. I mean, that was like key. Well, it was really worth it because I learned a lot. So when I arrived there at the firm lab for my sandwich program, Dan Hooper's student was Chris Calso, who was working on direct detection precisely. So he didn't work on anything else but direct detection of dark matter for low masses. That was his PhD thesis. Search for low mass directed dark matter using direct detection. That was his thesis. Okay. If you ask him the indirect detection, no, I don't know. But direct detection, I know. Collider, I have no idea. But direct detection, low masses, I'm the expert. So when you have a large group, that's what you do. You focus on a point. Okay, so and this figure you see there is from his thesis. Okay, so I borrowed from him. Actually, I basically stole it, but it's fine. I say, hey, can I get the figure from your paper? I say, yeah, sure. Just tell it was mine, and that's what I did. So I put in my thesis his figure. So what it's showing is the following. What we just concluded. So in the y-axis, I have the minimum velocity, and the x-axis, I have dark matter mass. Remember, the y-axis is what is the minimum velocity required for some dark matter particle produce a signal of a given recoil energy. Okay? Whatever that would be. And then you see is the following. So if a dark matter mass, if the dark matter particle has a mass, so let's just write down also on top of this the formula. V min is m, okay, I'm gonna write here. V min square root mu ER over 2, right? Is this? Yeah, 2 m squared. 2 m squared, and on top there's some mn. Okay. Mass of the nucleus. Okay, so now look at this. So let's fix ER. Let's assume that all detectors they all have the same energy threshold. All of them have the same ER. Okay? So just look at the formula. remember, mu is the reduced mass, is the product divided by the sum, okay, of the dark matter mass and the nucleus. Here's the definition. I wrote it here. Let me zoom out. Here, the product divided by the sum, okay? Dark matter mass and the nucleus. Now look at there. What you see is the following. I fixed the recoil energy. So it means is, let's pick a dark matter mass of 10 GeV. So I'm going to write now a vertical line here. 10 GeV. There. So if I have a 10 GeV dark matter particle, I need that dark matter particle to have at least 700 kilometers per second in order to produce a recoil energy that I can see. Okay? If the dark matter happens to be 20 GeV, then she doesn't have to have such a minimal velocity. It should be around 400 to produce a signal. If it's 40, it would be this value. But look, this is for xenon. Xenon has a mass, atomic mass of 131. So the larger the mass, the larger the min. See here, Mn. The larger the mass, the larger the min. So heavy targets require large minimal velocities. So from this reason only, you see the following. If I have a very large, heavy target, such as xenon, remember the maximum velocity I can have is 500 something plus 200, right? So I say 800, let's call it 800. So it's very hard to see, is unlikely that xenon will see a dark matter mass below 10 GeV. Because he's gonna just a very small probability, right? Just because of distribution velocity, just velocity particles at the tail of the Maxwell-Boltzmann distribution can produce a signal at the xenon detector, if the mass happens to be 10 GeV. Okay? Fine? However, if I use light targets, such as sodium, has atomic mass of 23, then look at the difference. For 10 GeV, the one in blue, here, I get less than 400. Less than 400, I already see it. So I can get a large portion of the Maxwell-Boltzmann distribution, almost all of it. It's still going to produce a signal that I can see using sodium. From this figure, I conclude that I don't know what the dark matter mass is. I have no idea. If it's heavy, okay, everybody can see it. Because look, as I go to heavier masses, I don't need much velocity, large velocities. But for light dark matter masses, I need light targets. Okay? So what happened is, as I don't know what the dark matter mass should be, let's say I believe the dark matter has to be light. What I'm going to do, I'm going to use a target at which the atomic mass is small. Because we will enhance the probability of me finding a signal. Because the velocity distribution is a Maxwell-Boltzmann-like. If the velocity distribution was just a flat curve, then it wouldn't make any sense. Okay? But it's not a flat curve. Make sense? And why I'm going to say this? Because you're going to see in the next lecture, because at around 2014, a signal was observed for very light dark matter particle. No, cogent. 2013. Was around 2012 and 2013. Cogent was a detector. I'm going to cover in the next lecture. Observe a signal consistent with 10 GeV dark matter particles. And that's when this whole discussion came. So what I'm explaining to you today, you think this is so basic, everybody knew. No. There's a research. There's a research from a physicist different in 2013. Okay, so it's something 10 years ago. So all these things that sounds okay, that sounds easy for now. I just see the formula. But this is a research that was developed 10 years, 12 years ago. Okay, so now it's in books, but it was 2 years ago, 12 years ago. So they observe a signal consistent with a dark matter of 10 GeV, but the xenon detector did not see it. I said, look, no, it's not possible, because how one detector doesn't see it and the other does? It's the same mass, it's the same dark matter particle. Why one sees it, the other doesn't? No, it's just a fluke. Fluke is a statistical fluctuation. No, it's just a fluke. No, this is just some error. Somebody screwed up, made a mistake, because that's not possible. The same mass. If you saw, I should also see it. No, you shouldn't see it. It depends on the mass of your target. You see? It's very unlikely that the xenon would observe that particle. Okay? And that's like, if you absorb this, you're saying that a detector way more advanced than Cogent, which it is. Xenon was much more advanced than Cogent, as you're going to see in the next lecture. Did not see something like they had a detector made of 8 people. 8 people get together and made a detector, and that was the Cogent. And that was in the basement of the University of Chicago. That was the Cogent detector, the basement of the University of Chicago. And I said, what's going on? What the hell? How can they have a small detector, really small? You're going to see the pictures like this big. Now they observe a signal consistent of 10, and the guy with 200 people in a collaboration, 3,000 meters underground, did not see anything with way more advanced. Are you crazy? And that's when the whole discussion came. Chris also was from the University of Chicago, from the same group of those guys who detected. And I said, no, but there is an explanation for it. It has to do with the velocity distribution. That's it. I'm not making up something, you know. We all assume that it was Maxwell boson, right? It's non-relativistic. So they should not, doesn't have to see it. It's okay if it doesn't see it. However, let's use targets with a mass similar to germanium. Look at germanium. Germanium is around 200 something. And the reason why you see this reference is germanium is heavier, right? So the curve should be above the blue one, right? The reason why it's not above, because I'm already including the fact that the energy threshold for germanium detectors is smaller. So it compensates a bit, okay? Because if I just decrease Mn here, if I just decrease Mn, I should decrease Vmin, right? So it should, the one in red should be above, because it's larger, above the blue one. Blue is this one, okay? But it's below. It's below because the energy threshold, ER, was below the one for sodium, for the one for xenon. So it compensates a bit the mass. That's why it's below. And the Cogent detector claimed to have a much lower threshold. I said, no, it's for 2 things. First, the velocity distribution explains it. And second, the energy threshold for Cogent is much smaller. That's why they saw it and you didn't see it. So it's not your fault. It's simply because of the velocity distribution. Okay? Okay, so I think it's time to go because I have to teach now for 3 hours straight. Okay, and we're going to see these experimental aspects in the next lecture. All right, guys. See you all tomorrow.